Hello. I'm going to try and justify the small angle equation that I've used in several of my previous videos, particularly the physics style videos. What the small angle equation is, if you haven't heard, I've written it mathematically here. It's basically the sine of an angle, as the angle becomes very small, is approximately equal to the angle itself. And in fact, in the limit, as x tends towards 0, sine of x actually becomes x. So this small angle equation is used in a lot of very interesting physical approximations, such as simple harmonic motion. You can have a look at that video at your convenience. I've written out a second one for cosine x actually. And again, as x approaches 0, cosine x becomes 1. And this one's much easier to sort of visualize, because if you substitute 0 into that equation, well, if you substitute 0 into y equals cos x, you get cos of 0, which of course is 1. So this second one is much easier to sort of think about than the first one. So I'm going to be concentrating on justifying the first one. Before I do, I'll just point out that you can generate a third small angle equation in terms of tan x. I think I've actually used this one in my simple harmonic motion video. And the way you do this is you express tan x in terms of sine x over cosine x, which is actually the definition of tan x anyway. So that shouldn't be too much of a surprise. You can express the limit of a quotient actually as a quotient of limits like this, so you can split that up like that. And then I've just substituted these results in here. So obviously the answer is x, and you notice that the limit as x tends to 0 of tan x is actually the same as the limit of x tends to 0 of sine x. So again, that's fairly useful to know. Anyway, I'm going to start off deriving the first equation now using a graphical method. And what I've done is I've drawn out the red curve here is actually y equals sine x, and you see the magenta line is y equals x, and you can see very clearly that as the angles become smaller and smaller, the equation y equals sine x, or the curve representing y equals sine x, becomes much closer to the line y equals x. So you can see that sine x becomes like x as you get closer and closer to the origin. So that's a geometrical a graphical interpretation of it. And you can do the same for cosine x, and that's the green curve here. That represents y equals cosine x, and again that approaches the line y equals 1, as I said here. Anyway, I'm going to start with some more algebraic methods now. And the first one is a very commonly seen justification, and that's writing my function as a power series. And this is a general Taylor expansion. That I can write my function as an infinite polynomial of increasing powers. This is a famous result, so I'm not going to justify it here, but I'm just going to write down the result. A is at any point on the function that you wish to approximate your curve by, and as you increase the number of terms you have in this series, this expansion becomes closer and closer to the original curve around that point. So at x equals a, it'll give the same value as f of a, obviously because f of a is equal to f of a here. So as you add more terms, the curve becomes a better approximation at points that are further away from a. So in this case, I'm going to let a equal 0, which is a very reasonable substitution to make, because I want to approximate my curve at the point around a equals 0, x equals 0, of which is of course equal to a. So I'm going to let my function be sine x, and I'm going to let a equal 0. And what I'm going to do is I'm going to write this as this infinite series of polynomials. What I'm first going to do is actually express, is create a new function, and this is just sort of to help me quickly calculate some derivatives of sine x. You see these things here. This is basically this term here is the derivative of f of x evaluated at a, and you can see that I'm going to need to calculate a large number of derivatives. So what I'm going to do is I'm going to find an algebraic expression that will allow me to calculate the derivatives easier, and this is not entirely necessary. It's probably easier if you just go through the methodical process of calculating derivatives, but this is just a nice piece of mathematics that is just fairly interesting anyway. So this is my expression for it, and I'm going to show why this is. So this is a multivariable function in terms of x and n can take any positive integer values. of course x can take any value. So I've used the addition formula here to expand out my u of x and n. So I've expanded that out and using my addition formula like this. So just you might want to look that up if you don't know what the addition formula is for sine x. So anyway, that's very straightforward. And you can see that this, if you start substituting values into here, values for n, so you can start substituting values for 0, 1, 2. So n equals 0 represents 0 derivative, or basically the function itself. N equals 1 represents the first derivative. So we substitute these values in, you find that we can define this function in terms of these 4 different functions depending on the value of n. And actually you will see that these are the derivatives that you would get if you were just doing it methodically, and it's basically a repeating pattern. And I've expressed this repeating pattern in terms of a new integer which I've defined as m. So you can check this works for yourself. But for any integer value of m, each of these 4 equations will satisfy that value. So if n equals 1, that has a value of m equaling 0. So you can see that n equals 1 is the first derivative of sine x, which is cos x. So again that works clearly. So for n equals 1, you get cos x, and also you get cos x for n equals 5, because if you let m equals 1, 4 times 1 is 4 plus 1 is 5. So again, you can just see that this is a repeating pattern. So this is basically an equation that calculates derivatives of sine x. And of course you could do it for cosine x as well, because cosine x will just start in a different place. It will start one place further ahead. So again, this is how to find my function as u of x and gain the derivative of sine x. So that's fairly straightforward to see, I think. So all I've done here is I've just substituted these results into the original expansion. So obviously I've put this Taylor expansion in terms of an infinite sum here, which is just an easy way to represent it. I've left a equals 0, so you can see I've just got x to the m because a is 0, and I've let my equation for the derivatives, I've replaced that with u of x m, because that's the function I've used to calculate my derivatives of sine x. And of course this is evaluated at 0, so which is why I've got 0 here. Actually, yes, this is evaluated at x equals 0. So that's very straightforward there. And you can see that for increasing values of n, we go through each of these derivatives like that. So that makes good sense. So all you have to do now is just well, what I've done here is I've expanded this sum and shown you the first few terms using my Taylor expansion. So that's how I've done that. And it turns out that you get x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on. And you can calculate more and more terms if you want to, using this summation that I've got here with my function of u of 0n. So what I've done here isn't entirely necessary again, but it's just rewriting this Taylor expansion in terms of a neater way. So basically, this term here is basically sine x written as an infinite sum. This term here represents sine x. Obviously, as does every other term that I've got in this section, but that's just another way of writing sine x if you haven't seen sine x written like that before. Okay, so back to the proof that I was going through. So if I want the limit as x tends to 0 f of x, I can write the limit of this thing here that I've written here, which the expanded version of the sum is also written like this. Now you'll notice that if you substitute x equals 0 into this, you get 0, which is not really what I was wanting to show you. But it's not totally unreasonable, because obviously sine of 0 is 0, and it also and obviously as the angles of sine x become smaller, you are getting closer and closer to 0. So this is also correct. So the answer of 0 is not wrong as such. But in order to prove the small angle formula as well, we need to do a little bit of manipulation. So what I've done is, instead of writing the limit of x tends to 0 f of x, I want to rewrite it as the limit of x tends to 0 f of x over x. So writing that out as my series that I've just shown you how to do, that we can write the series obviously as this and then divide it through by x. And obviously the x cancels out with this x to produce 1, and obviously the powers will decrease. So instead of odd powers, you're going to get even powers, like that. These terms obviously are irrelevant when you substitute x equals 0 because they all go, and you end up with 1. So the limit of f of x over x as x tends to 0 is 1, which, as you can see, so okay, I've written basically what I've done here is I've shown that you can write the limits of a sum of limits. So again, the only term that's going to remain is this one on the left here, because all of it's going to be 0. So what I've shown is the limit of x tends to 0 of f of x over x is 1. So if we multiply this through by x, we can see that the limit of f of x is x tends to 0, which is the limit of x as x tends to 0 sine x, because that's what I define my function as being x. I don't know why I put 1 there, but that's x. So you can see that this is mathematically consistent. Okay, I'm going to show a third justification. I think this one's more common, but it's called the mean value theorem. In fact, the Taylor's theorem that I've just used is actually somewhat of a more sophisticated version of the mean value theorem, but I haven't proved the Taylor expansion. So instead, I'm going to just show how you might use the mean value theorem to also justify this. Although I should point out this is more justification than a proof, because this is not a formal proof, but it at least shows you why it might be reasonable to believe this. So I've first of all written out the mean value theorem here. It looks complicated, but it's actually a very simple idea. So I've got, for a is less than c, there exists a value b. So these are just points on any graph y equals f of x. So these are just x values. These are just points. So for any a less than c, there exists a value b such that the derivative of the function evaluated at b is equal to f of c minus f of a over c minus a, where a is less than b is less than c. Again, this might sound complicated, but I'll try and explain what it means. This thing here is basically a tangent line where you might take. So let's have a look at this function here. So ignore the dotted line on the top. Just look at this one here. So what I might do is to ignore the bottom one. Look at the top one. It's probably easy to see. So this might be my point A, and this might be my point C. So if I wanted to draw a tangent line that approximates this curve, obviously it doesn't approximate it very well, but if I wanted to approximate the curve by drawing a tangent line, I could draw it through this point here, and this would represent the gradient. What the mean value theorem says is that there exists a point B somewhere in between A and C, where the gradient of the actual curve itself is the same as this tangent line. So there will be, on this curve here, a point where its instantaneous gradient, so it might be around here, is the same as this tangent line. And this is for any values of A, B, this is for any values of A and C, there will exist at least one value of B. And this diagram here is sort of trying to give a geometrical interpretation of why this is. If I have a function, then I can what I'm going to do is if I have this straight line here, this straight line is a tangent line on the function. So there are three different types of curves that we could have that could be approximated by this tangent. We could have the straight line itself as the function, in which case, of course, there exists a b, because every single point has the same gradient as the line itself, because the line is the function. And then there are two other types of functions. There's one that goes above the line and one that goes below. The one that goes above has an increasing gradient at first, but in order to rejoin the line, its gradient must then decrease. So, providing that this is continuous, since we have an increasing gradient, then the gradient must decrease in order to reach the line again. So obviously there has to be a point at which the gradient is going to be identical to this tangent line. But of course the other type of function is the one that decreases at first and then increases again. You can probably think of other kinds of function that might come down and go back up again. But broadly, that's no different, because it's going to go up and then come back down and then go up again. As long as the function starts at this point and ends at this point, there must be at least one point in between where the gradient is the same as the tangent line. So it seems a fairly intuitive geometrical reason why this might be. So what I'm going to do is I'm going to use this mean value theorem. I'm going to let f of x equal sine of x. So we can say that there exists a b such that the derivative of the function with respect evaluated at b is equal to sine c minus sine a over c minus a, which is cos b, obviously, because the derivative of sine x is cos x. So this makes sense. Now I'm going to define values of a, b, and c. Just to try and make this useful. So I form this inequality here. So you can see that a is greater than or equal to 0, which is less than or equal to b, which is less than or equal to c, which is less than or equal to pi over 2. And the reason I've made all this less than or equal to pi over 2, although I could actually have used value greater than pi over 2, is that for this sort of range, if we look at cos x again, if we look at values between 0 and pi over 2, you can see that cos x is always decreasing. There is never a point where cos x increases in this range. I mean, actually, you could go even further and it's still decreasing. But in this range between 0 and pi over 2, cos x is never increasing. That's the important thing. So, given that, we know that a is less than b, less than or equal to b, is less than or equal to c. We know that cos a is going to be greater than or equal to cos b, is going to be greater than or equal to cos c. And then we can use this result, so we can say that cos a is greater than or equal to cos b, but instead of writing cos b, we can substitute in the result from the mean value theorem, which is this, greater than or equal to cos c. Now, what I'm going to do now is let a equal 0, because again, a is allowed to equal 0. I'm considering values between 0 and pi over 2. So I'm just going to let a equal 0. It's not even a limit, it's just evaluating as a equals 0. So if I let a equal 0, you see that cos a becomes 1. You can see that sine a is obviously 0, and this a becomes 0. So this simplifies to sine c over c, and then cos c here. So what we've got is 1 is greater than or equal to sine c over c is greater than or equal to cos c. Now the next stage requires a little bit of sort of pre-knowledge. You've got to assume that you know that as c tends to 0, cos c tends to 1. Basically, I'm sort of using this second small angle equation to justify this first small angle equation. But it's fairly reasonable, because this second one is much easier to understand why this is true, because you can substitute cos of 0 and you'll get 1. So I think it's okay to do that. It's just a justification. So as c tends to 0, we've got that 1 is greater than or equal to sine c over c is greater than or equal to 1. So this thing here is going to be in between 1 and 1. Of course, the only value that it can take is therefore 1 itself. So we've got sine c over c is equal to 1, as c of course tends to 0. And then multiplying through by c, we can get sine c equals c, and that's as c tends towards 0. I should point out that this is not a mathematically rigorous argument, but it's a reasonable justification, and the point is it's consistent. It works as it should do. And also, again, Taylor's theorem, which I've used here, is actually a more sophisticated version of the mean value theorem, but proving it is obviously more complicated, so I won't go time to go through that. Anyway, I hope this has been a reasonable justification for the small angle equation that I keep using throughout my videos. Please put any comments if you think I've done anything wrong, or would like me to do anything else in particular.